Hello, I'm Bhavesh and I will be presenting on accelerometers. So first, what is an accelerometer? It is a device that transforms mechanical acceleration into an electrical signal. Its main function is to measure the velocity change rate or the force exerted on an object and generate a corresponding output signal that's directly proportional to the acceleration. This signal can be leveraged to track the movement, location, and oscillation of the object, as well as to regulate other equipments or systems based on that data. Accelerometers have wide range of applications. Accelerometers are used in vehicles to measure the acceleration, deceleration, and lateral forces, and to trigger airbag deployment in the event of a collision. They are also used in smartphones, tablets, and gaming devices to detect the orientation, tilt, and motion of the device. They are also used in wearable fitness trackers and sports equipment to track movement, monitor activity levels, and calculate calories burned. They are used in robotics to detect changes in orientation, motion, and position. They are used in industrial equipments to monitor vibrations and to detect fault in the machinery. They can also be used in the aircrafts to monitor the vibration, motion, and orientation of the aircraft and its components, and to provide feedback for flight control systems. Accelerometers typically consist of a mass suspended by springs or some other form of flexible element within a casing. When the accelerometer experiences acceleration, the mass within it moves in response to the applied forces, causing a displacement related to the casing. This displacement is then measured by a sensing element, typically a piezoelectric crystal, strain gauge, or capacitive element, which generates an electrical signal proportional to the acceleration. Accelerometers can be classified in mainly two categories based on their mode of operation. The first one is piezoelectric accelerometers, the second is capacitive accelerometers. MEMS, that is micro electromechanical system, is nothing but capacitive based accelerometer, as we will be seeing in the coming slides. Piezoelectric accelerometers utilize the piezoelectric effect, where certain materials can produce an electric charge when exposed to mechanical stress, such as quartz or ceramics. The sensing element in these accelerometers is a piezoelectric crystal, which is mounted on a mass that moves when subjected to acceleration. As the crystal deforms due to the mass movement, it generates an electric charge proportional to the acceleration. An amplifier circuit is connected to the crystal to measure this charge. These accelerometers can detect extremely small accelerations, even as low as a few micro G, owing to their high sensitivity. The following clip demonstrates the working of piezoelectric accelerometer. Acceleration causes mass to move, deforming the crystal. Deformation generates charge on the crystal. Amplifier circuit measures this charge and converts it to a voltage signal. The voltage signal is then further processed to calculate acceleration. Piezoelectric accelerometers possess several advantageous features, including high sensitivity, enabling them to detect even minute accelerations. These accelerometers are capable of operating across a wide frequency range, making them versatile for use in numerous applications. They can function effectively in high temperature environments up to several hundred degrees Celsius. Furthermore, they have low power consumption, making them ideal for integration into battery powered systems. Piezoelectric accelerometers are also compact and lightweight, making them easy to mount and integrate into different systems. A capacitive accelerometer comprises two parallel plates with a tiny air gap between them, wherein one plate remains stationary while the other is suspended on a spring. When an acceleration is experienced by the accelerometer, the movable plate moves due to the force, causing a change in the distance between the plates. This alteration in distance leads to a change in capacitance between the plates. As capacitance is inversely proportional to the distance, the change in capacitance is proportionate to the magnitude of the acceleration experienced. Typically, the accelerometer generates an electrical voltage output which reflects the change in capacitance. This output signal can be utilized to measure the acceleration in the accelerometer's axis. Capacitive accelerometers can be designed to measure acceleration along one, two, or three dimensions. Step-by-step working of capacitive accelerometer is as follows. There are two parallel plates, one is stationary, other is movable. Acceleration causes one plate to move relative to the other plate. This change in distance causes change in capacitance. Output signal, which is typically a voltage signal, is proportional to the change in capacitance. This signal is then processed to quantify acceleration along the axis of accelerometer. Capacitive accelerometers offer several benefits, such as high resolution, enabling them to detect even minute changes in capacitance for precise measurements. They can operate across a wide frequency range, making them versatile for various applications. Capacitive accelerometers consume relatively low power, making them an ideal choice for energy efficient applications. Furthermore, their small size enables them to be used in compact devices where space is limited. These accelerometers also offer high linearity, providing accurate and dependable measurements with minimal distortion. MEMS or micro electromechanical systems accelerometers consist of a tiny mass that is suspended on a cantilever beam, which acts as a spring. When subjected to acceleration, the mass moves relative to the beam, causing a change in capacitance between the mass and the electrodes placed on either side of it. This capacitance change is then converted into an electrical signal, amplified and processed to calculate the acceleration. One of the significant advantages of MEMS accelerometers is their size, which can be made very small using microfabrication techniques. This miniaturization enables the production of highly compact and low power sensors that are ideal for applications where size and power consumptions are critical factors, such as mobile devices or wearable technology. Moreover, some MEMS accelerometers incorporate additional features such as temperature compensation, self-test capabilities, and onboard signal conditioning to improve their performance and reliability. Temperature compensation is used to minimize the effect of temperature changes on the accuracy of the measurements. Self-test capabilities allow the device to perform an internal diagnostic test to ensure that it is functioning correctly. Onboard signal conditioning refers to the amplifier circuitry that is included within the accelerometer, which amplifies and filters the electrical signal generated by the device to improve the accuracy of the measurement. The video clip demonstrates the working of a typical MEMS accelerometer. A small mass is suspended on a cantilever beam, which acts as a spring. When accelerated, the mass moves relative to the beam. Movement of the mass causes change in the capacitance between the mass and the electrodes placed on either side of it. The change in capacitance is detected and converted into an electrical signal. This signal is then amplified and filtered to remove noise and unwanted frequencies. The filtered signal is then processed to provide measurements of the acceleration along the axis of accelerometer. MEMS accelerometers have gained popularity due to their unique features, which make them suitable for a wide range of applications. One of the most significant advantages of MEMS accelerometers is their compact size, which is the result of microfabrication techniques used to produce a miniature version of the mass spring capacitance system. This feature makes them ideal for applications that require miniaturization, such as mobile devices or wearable technology. Another advantage of MEMS accelerometers is their low power consumption, which is a result of their small size and efficient design. The low power usage makes them suitable for portable and battery powered devices. Additionally, MEMS accelerometers are highly sensitive and can detect even small changes in acceleration. This high sensitivity makes them useful in applications where precise measurements are necessary, such as in navigation systems. MEMS accelerometers can measure accelerations across a wide frequency range, making them suitable for various applications. They provide accurate and reliable measurements with high resolution, making them useful in scientific and industrial settings. Moreover, MEMS accelerometers are easy to integrate into existing systems, and their small size makes them suitable for using complex systems. All of these features make MEMS accelerometers a versatile sensor technology with a wide range of applications in different fields. Multi-axis accelerometers are sensors that are capable of measuring acceleration along multiple directions, which distinguishes them from single-axis accelerometers that can only measure acceleration in one direction. By measuring acceleration in two or three perpendicular directions, Multiple axis accelerometers can provide more comprehensive information about the motion and orientation of an object, which makes them ideal for various applications, such as inertial navigation systems, motion tracking, and vibration analysis. They are exclusively used in automotive, aerospace, and industrial applications to monitor the movement and behavior of objects in real time. Multi-axis accelerometers may encounter issues that can compromise their performance and precision, similar to an electronic device. Cross-axis sensitivity is a typical concern for multi-axis accelerometers, as they are designed to measure acceleration along several axes and can also detect acceleration from other axes, resulting in decreased accuracy. Calibrating the accelerometer to minimize or eliminate cross-axis sensitivity can be a viable solution. Noise interference from the environment is another problem that can affect accuracy, and using noise filtering techniques and shielding the accelerometer from external interferences can help mitigate this issue. Multi-axis accelerometers can also be sensitive to their orientation, leading to varied output based on their positioning. To tackle this problem, the accelerometers can be calibrated in multiple orientations to account for this orientation sensitivity. Accelerometers are basically sensors used to detect acceleration. We can broadly categorize accelerometers based on their mode of operation: capacitive and piezoelectric accelerometers. Capacitive accelerometers use change in resistance to quantify the acceleration, while piezoelectric accelerometers use piezoelectric properties of certain crystals to quantify acceleration. We also looked at MEMS, a compact system that is based on capacitance. Finally, we looked at multi-axis accelerometers. They are capable of measuring acceleration along multiple axes. Overall, accelerometers are important sensors that provide critical information about motion and acceleration in a variety of applications. Thank you.